All right, good afternoon, everybody. I'm going to break this up a little bit into a couple of pieces because this is a lot of material. And this, I'm going to be discussing protein structure, specifically narrowing my scope to the discussion of primary and secondary structure. So with that said, there are a couple of different levels of protein structure. Those levels are, one way you could think about it as your lowest level, your primary. That is just the sequence of amino acids. That's represented by A here. Excuse me, your secondary level is going to be local structures, represented by this right here. Excuse me, your tertiary is the overall 3D structure of a protein. And then your quaternary structure is the organization of a protein. So here what we have is a model for hemoglobin. Hemoglobin is a tetramer. It's also a homodimer. And what it consists of is two alpha subunits and two beta subunits, hence a tetramer. So what all of these polypeptides look like in three-dimensional space give you the quaternary structure of this protein. Now, what's very important whenever we think about protein structure is what are the different forces that kind of solidify these different structures. So your primary structure is determined solely by the covalent bonds, your peptide bonds. So those peptide bonds that connect one amino acid to the next amino acid. Your secondary structure is determined predominantly by backbone hydrogen bonds. So this is kind of a hierarchy in that, well, your secondary structure obviously has peptide bonds, but what is going to give you a structure like this right here? What's going to give you that structure is the backbone hydrogen bonds. So that would be not R groups, but instead the backbone of any polypeptide. Your tertiary quaternary structures, those are going to be determined by side chain hydrogen bond ionic interactions, as well as van der Waals interactions and hydrophobic interactions. So if you look at this model shown below, only these helical structures are really secondary structure. Everything outside of that, every other model shown here would be, or actually, no, I stand corrected. So these two, sheet structures and helical structures are secondary. So I will write secondary. And then everything else would be tertiary. I'm going to say and or quaternary. So all of those structures there are going to be dictated by R group interactions. Now, peptide bonds, as we previously talked about, peptide bonds are stable. They can endure prolonged exposure to a strong acid or a strong base, even at elevated temperatures, but only whenever you have that combination of super high temperatures and super high concentrations of an acid. And I'm talking something like 100 degrees Celsius plus 6 molar HCl. So super concentrated, strong acid plus high temperature is going to be what breaks a peptide bond. Now, this is just a model that shows the organization of different amino acids. The structure of a peptide bond, which we've looked at a little bit previously when we were talking about amino acids and drawing them out. The structural properties of the amide or peptide bond are very important for the overall structure of the proteins. A peptide bond is going to have two different resonance structures. And because it has these two different resonance structures, they're going to have partial, about 40% double bond character, and therefore they're going to be fairly rigid. So this model right here is how you've probably previously drawn them, but since it's resonance stabilized, it can go from this end all the way to this end. Now, what that ultimately means, this is an uncharged, but it is a polar entity. The nitrogen is going to be partially positive and the oxygen is going to be partially negative. So when people talk about a peptide bond, though, just for specifics, they're talking about this right here. Now, with that in mind, though, we talk about peptide bonds, we do kind of extend that to talk about a couple of different atoms within a peptide bond. Now, the structure of the peptide bond, as we now know, is first described by Linus Pauling in 1939. Linus Pauling was such an influential scientist because he made these huge discoveries tons of years ago. With the DNA double helix, he was hypothesizing that it was a triple helix, so that was a very popular opinion at the time. So brilliant guy. Due to the double bond character, the 6 atoms of the peptide bond group are always planar. So that means they all kind of exist in the exact same plane. So to illustrate that, here we have the peptide bond that I pointed out previously. But then those 6 atoms, we've got this alpha carbon, this other alpha carbon, our carbon and our nitrogen within that peptide bond, and oxygen and a hydrogen that are found either on that carbon or that nitrogen. Now, what that means is that those 6 atoms, they're not really going to move around. Like, you're not going to have some dramatic flexibility within this. Instead, they're going to exist in one amide plane. Now, with that in mind, though, we do have some rotation about a peptide bond. So what that means is that twists and turns can occur about either of the bonds linking the alpha carbon to the other atoms of the peptide bond. So this right here or this right here. So we can have twists with those 2 bonds. So alpha to the carbonyl carbon or alpha to the carbonyl nitrogen. Now, the dihedral or torsion angles describes the conformation of the entire peptide backbone. There are 2 angles per peptide plane, okay? So these angles are going to be, they are recognized and referred to as a phi and a psi angle. Now, the phi angle describes the rotation about the N to C alpha bond and involves the CO and C. Okay, so whenever I'm writing a polypeptide, I'm going to write it like this: N, C, C, N, C, C, N, C, C. There's a tripeptide. I haven't filled in all of the atoms, but I know my alpha carbons. And so what I'm going to do is I'm going to focus on, where is my phi angle? My phi angle is this right here, N to C, N to C, and typo, N to C. The other bond, however, is my C to C, and that is the psi angle. Then the bonds that have no label, well, those are C to N, my X. Or I'm just going to write out what this is. This is my peptide bond. So the bonds that are adjacent to my peptide bonds, those are my psi and phi, respectively. Okay, so that's helpful for me. There's tons of phi angles, there's tons of psi angles. I'm going to erase all of this. I'm going to move forward. The psi angle describes the rotation about the C alpha to carbonyl carbon and involves all of those atoms. Now, what's important about this is that those bonds can rotate, and there's favorable pairings of those rotations. Some values of phi and psi are more likely to occur than others. And those bonds that are more likely to occur, or those bond angles that are more likely to occur, are going to appear on this graph right here, which is also known as a Ramachandran plot. So what we have is all of this white space are regions in which a bond angle pairing are unfavorable. So to illustrate that, you're unlikely to have a psi of 90 paired with a phi angle of -90. So that right there is unfavorable. And so that's ultimately what these can be used for. I'm going to go ahead and stop this video. So I'll catch you up in the next one.